Really now. Yeah. Hold on. Yeah. You know, those brown chicken that's like honest. Honestly, there's the word with kind of. And then with the one like. Okay, so any questions before we get started? So on the board, I break down the things that I want to mention before I check into today's material. Okay, so I think on last Thursday we went through a few concepts for chapter 18, right? So the first thing we actually bring up is actually do we know how to write out the atomic symbol? Okay, so these are actually the things we're going to use over and over again for chapter 18. Okay, where the X is actually the letter symbol, A is the mass number, Z is actually the proton number. Okay, so proton is positively charged. The mass number is the sum of your proton number plus your neutron number. Okay, so those are the things that we must have in the very beginning. So for today, what we're going to do is actually we're going to tell you how to predict. If I give you one atomic symbol, okay, can you predict the stability of land nucleus? Okay, so that's actually a big part of the question of what we encountered for chapter 18. If I give one atomic symbol, okay, can you predict is stable or not stable? Okay, so if it's not stable, then okay, this actually, I mean, yeah, okay. So that's actually the first thing we actually start to learn for this chapter 18. Okay. Want to know whether things is actually stable or not. Okay. If it's not stable, it's going to undergo some decays, right? Then what kind of decays that we can actually have for the atoms? Okay. And once you know it's going to decay, once you know what kind of decay you're going to have, then the next thing also actually calculate for this chapter is what's the decay kinetics. Okay, so this is actually decay of a single atom. Then the only equation that we need to actually use for chapter 18 is this first order decay rate law, which we learned it before. And but we're going to get ourselves familiar again with this specific equation to do the calculation. Okay, so if you actually know how to actually use this equation, then you can understand how scientists using carbon-13 to date a subject. Okay, so many times you are going to hear something that, okay, these things has been revealed for thousands of years, right? But we don't have a very, only live about 100 years, right? How we actually know it's actually 1,000 years old. Okay, so that's actually a very scientific way to actually date every single subject you can see in our daily life using this simple equation. Okay, and we're going to go through one or two questions like that today. Okay, so talking about decay, first we can know a few specific particles. Okay, so the particle I mentioned, actually write down these particles here: alpha, beta, gamma, and positron. Okay, so every time you heard this term, alpha particle, atomic symbol wise, what it means is actually this helium 2,4. Okay, you have two photons overall. Mass number is actually 4, and you have two photons, two neutrons. Okay, and then the other one, beta particles, is nothing special but your electrons. Okay, so every time you heard the things beta decay or beta particles, what it means is just an interaction between what the atom you're talking about with one electron. Okay, so that's what beta particle means. Gamma particle, okay, so it's not very accurate. Gamma is actually the gamma radiation. Okay, it's like a high energy electromagnetic wave. Okay, it's just a way that the nature carry the energy in the form of electromagnetic wave. Okay, everybody understand what I'm talking about? Electromagnetic wave. Okay, what is actually the things you see every day? It is electromagnetic wave. The light. Okay, so different emissions. Okay, it's actually a kind of form. It's one form of energy. Okay, and different wavelengths show you different energy yeah, and represent different electronic or vibrational rotational behavior. Okay, we went through this energy landscape in the past lecture. We did not. Okay, good time to do that. Okay, so the most famous, the one we see every day, okay, the light we see every day, we call it UV visible emission, right? So what is that is actually a specific energy range, right? So wavelength wise, going from 350 all the way to 700 nanometers. Okay, so that is actually the wavelength I'm talking about, right? What is actually the most sensitive wavelength our eye is? Which wavelength that our eye is most sensitive to? What kind of light? Because color, what kind of color we actually most sensitive to? You guys have no idea? Interesting. What is actually thinking to see every day when you drive? Traffic lights, right? So what is actually the line that you know you can go? Green. Green light. There's a reason for why green, because our eyes most sensitive to green. Green yellow is actually the color that our eye, human eye, is most sensitive to. Okay, so many of these lights in your daily life has a reason. Okay, because it's more sensitive, therefore you know. Once you see that, you know you can go. Okay, so all the things we're talking about is UV visible light. Okay, it actually corresponding to specific processes of nature. Okay, the things we're talking about, all this is actually related to the electronic transition processes. Okay, so maybe it's actually too much for you guys, but you guys familiar with this ground state, excited state type theory? Okay, so every time we say some subjects got excited, who is excited state, right? What is excited? What has been excited? What is the things that got excited? It's your electron. Okay, so every time through this ground state to excited state, okay, that is typically referring to the electrons. And all current translation has the energy range in the UV visible range. Okay, so that's actually a good thing to know because there's actually another thing that you know so and use it every day is the microwave. Okay, can we see microwave? We cannot see microwave, right? Our eyes only sensitive for a very limited region. Okay, microwave is actually too long for us to see. Okay, but microwave is actually high or low in energy compared to your UV rays. Low. Okay, much lower. Okay, so what is that energy range? What kind of motion that kind of energy is going to tell you? Every time it's microwave, right? How is the food got heated? What? Common sense. Okay, you should know this because it's actually fun. Okay, so microwave is actually related to what? The rotation, motion. Okay, so when you put your foot into your microwave, when you hit the button, okay, you're going to produce a lot of microwaves reflecting inside the cavity. Okay, so what does it do? It's going to make the molecules rotate like crazy. Okay, what kind of molecule I'm talking about? What's the molecule that you have in your food? Water. Okay, water is actually the one that heats things up. Okay, so how? Because the water is actually rotations doing this so fast. Okay, every time you do the rotation, you release your energy to what? To your environment. Okay, the molecules actually resistant. Okay, all the other things actually environment, right? So once I do things like crazy, what do? I release heat. Okay, just like if you do exercise. Okay, you're burning yourself. You put the fat inside you, and then you feel like there's a heat coming out of it. Okay, similar things, another to your water. Your water is actually doing this rotational motion so much that actually produce a lot of heat. Okay, and those heat will actually, let your food come out. Okay, so different kind of wavelengths corresponding to different motion. Okay, so we're just talking about the UV physics, the electronic transition. Okay, energy-wise, it's like this thing. Okay. Next one is what? Vibration. Okay, vibration of energy. What is actually the radiation we use? IR. Okay, so IR has an energy gap like this much. Okay, so you can see there's actually all those magnetic differences. Okay, so this is actually your energy gap. The interaction just UV visibly side. Okay, then for this vibrational motion of your molecule, the energy suddenly becomes this small. Okay, so if you use the IR to look at some absorptional excitation, you're doing excitation amount here. Okay, you're not going to use the UVs to excite this because energy is different, right? They are not in the same frequency. They are not going to resonate. Okay, they cannot talk to each other. Okay, how about the rotation? Rotation is like this candidate. Okay, you see that energy landscape is actually way too different. So we're actually using different wavelength light. You're looking at very different and specific processes. Okay, it's fun though, because right now you can actually say, okay, I want to excite the electronic at the same time, to excite some of the vibration, some of the rotation. Then you can use light to actually do all these things. Yeah, so it's actually very cool things to do. Okay, of course, like in your daily life, you won't be able to see those things. But that's where the science has built us the foundation. So we can understand many things behind the things we see every day. Okay, so it's actually a very cool thing. Here, Gamma radiation, okay, is just another form of radiation that carries actually huge amount of energy. Okay, so you need to know what when I say gamma particles, what it means is actually just a radiation carries a very extremely high energy. Okay, and the right last one we're trying to tell you is actually called the positron. Okay, what it really means is actually a positive electron. Okay, a very weird concept. Okay, because but this is comes out because scientists realize, okay, we know this actually something is charged. Its charge is just opposite to the typical electron. It doesn't have mass. Okay, we don't really know what it is. All the things we know is that it carries positive charge. Therefore, we name it as positron. Okay, so let's count the things how scientists start to name something. That every time we see something, right, we don't know what it is, but we can train it based on its property first. Okay, and later on, people will do more research and realize, oh, what's going on. Then we'll actually give a name that's actually more appropriate. Okay, but this actually involves the evolution of science development. Okay. All right, so we need to actually memorize this. Okay, helium is your alpha particle. Electron, that's the one charge, is empty mass. Gamma radiation, no charge, no proton, doesn't carry charge, doesn't carry mass. Okay, and positron is actually the one doesn't have the mass, but carry a positive one charge. Okay. Another thing that I found students always get confused is this. So I write this forward, decay, emission, capture, absorption. Okay, so these are the key words that you want to get familiar with. Okay. So if I say one atom is undergo a beta decay, okay, what I'm really trying to say is that your atom X is undergo a beta decay, exactly. It's going to undergo a decay, right? And then after decay, it's going to produce a beta particle. Okay. Therefore, if you write out a chemical equation, that beta particle will show up on the reactable product side. Reactable product side. Product side. Okay. Every time you see some species undergo certain decay, okay, then that decay particle will show up on the product side. Okay. There's actually another way of saying the same thing. Okay. The atom X is undergo a beta emission. Okay. Then you should put the beta particle on the product side again. Okay. So emission, decay, they are synonyms. Okay. It all means whatever particles mentioned will show up on your product side. Is that clear? Okay. Flip the point now. If I say I capture a beta particle, okay, or I absorb a beta particle, okay, then I should put the beta particle on the reactant side of the equation. Okay, so you can actually see that, because once you see that, then you can actually decide the question without any problem. All right. So those are the very important concepts. Okay, so I guess I need to write out this equation so you can see what I'm talking about more clearly. Okay. So this is actually the general equation that you're going to see. Okay, if you have an atom X to start with, it's undergo certain decay. Okay, so you're going to see this equation, right? So we should know that this will always be true, right? if you look at the mass numbers, okay, the mass number sum of your reactor must be the mass number sum of your product. Okay. Similarly, the proton number sum of your reactor must equal the proton number sum of your product as well. Okay, so this must be true. Okay, so let's actually the very important concept before we actually jump into the things we want to discuss today. Okay, any questions so far? Good? Okay, so let's talk about this. So we just finished this, right? That's actually the general equation form that you always need to know how to write it and use it. Okay. So the second thing we want to talk about is, I guess by now you should have a good idea about what's alpha particle, what's beta particle, what's gamma particle, what's positron. Okay. Stability is actually the things that we start to focus now. Okay. So if I give you an atomic symbol, how do you actually predict that is actually going to be a stable nuclei or not? Okay. So the rule number one, there's a few magic number that we need to actually memorize. Okay. So look at the proton number, meaning look at the Z. Okay. So if your Z is equals to 2, 8, 28, 82, 20, 50, 126. Those are the magic numbers. Okay. So let's actually not much reason I can give you. Let's actually the things we have observed so far. Okay. And then I write this way because it's easier to memorize. 2A, 28, 82 is a set. Okay, and then 20, 50, 126 is another set. Okay, so not too difficult to memorize. So every time if you see your proton number belongs to these few specific numbers, then they will be stable. Okay? But that is actually not the one you got asked most often. Okay. This is actually the one you got most often. Okay. So if today I say I give you atomic symbol, okay, and ask you to predict this is actually a stable nuclei, then what you need to compare is actually you need to calculate this first. The mass differences between your atomic mass and your mass number. Okay, so what's the difference between atomic mass and mass number? The mass number is whatever label on the atomic symbol, that's your mass number, right? Where did you get your atomic mass? Where did you get your atomic mass? Yeah, periodic table. Okay, so for all the numbers you see on the periodic table, those are the atoms in its most stable state. Okay, so they are, you can consider the periodic table is actually the most stable atomic symbol. Okay, and of course, you don't see integers in your periodic table, right? Because we have isotope. So your atomic mass from your periodic table is actually the average sum of all the nuclei in the nature. Okay, but no matter what, the most stable one will be the dominant one and reveal the numbers in your periodic table. Okay, so that's why in order to compare the given mass number to the atomic mass in your periodic table. Okay, if the differences is larger than 2, then it will be unstable. Okay. The other thing is actually if your proton number is larger than 83, Okay, besides the lecture number 126. Okay. If you have a proton number larger than 83, it will be unstable. Okay. So those are the things that we need to know first to judge whether a given nuclei is stable or not. Okay. So those are the first things that we want to actually learn today. Any question about this? Okay. So she's asking, okay, if you look at periodic table, you actually have more than 83 atoms, right? Yeah. What does that mean? That all the things after 83, they are not really stable. Okay. They are actually not existing stably. They decay. Okay. But in its very original form, people know there must be existence this substance. Okay. All right, so let's actually the first big things that we need to learn. So let's go through a few examples. Okay, first thing first. Is N17 stable or not? Okay, so how do you do this? So from here, you know, your mass number is what? 17, right? So we know the things we want to actually do is that check your PI table. Okay, so what is actually the proton number? 7, right? Everybody have your PI table with you, right? Okay. So what is actually the atomic mass? Now, from here, you can actually first know the 7 is actually not the matching one of the matching number, right? So my mic on? Is my mic on? Okay. Oh, that's why I feel like my voice is gone. Okay, so what is the atomic mass you can find from your periodic table for your nitrogen? 14, right? Therefore, when you calculate your mass differences, which is 17 minus 14, that's equals to 3, right? And it's larger than 2. Therefore, it is unstable. Okay. Second, arsenide 74. Okay. So what is the proton number of your arsenide? 33. Again, this is not one of the magic number, right? So you actually use in calculate the mass differences. Okay, so what's the atomic mass you get from your periodic table? 74.92, right? Therefore, you can calculate your delta N equals to 74 minus 74.92. Take the absolute values. You got 0.92, which is smaller than 2. Therefore, it is stable. Okay. Number 3, aluminum 24. Okay, what's the proton number? 13. Okay, atomic mass 26.98. Then you calculate your delta M, which equals to 24 minus 26.98, they give you 2.98, which is larger than 2, therefore unstable. Okay, the very last one, bismuth. What's the atomic number? What's the proton number of your bismuth? 83. Okay, atomic mass 208.9. Delta M equals to 209 minus 208.9 equals 2.1, smaller than 2, therefore stable. Okay, so this is actually how you predict whether a given nuclear ion is stable or not by using your delta N. Okay, any questions for this? Okay, so if not, let's look at the second question. Okay, so it says CF244 is produced as well as two neutrons when a nucleus reacts with an alpha particle. Okay, so this is actually a very standard question, right? So you need to actually see and write out the equation based on the description. Okay? So how do you do that? First, you need to know who is actually your product, who's your reactant, right? So the question apparently is asking you the reactant, right? So let's say we call that reactant X. Okay. So you have a atomic, we have the mass number A and then the proton number Z. Okay. So we say when a nucleus react with alpha particle, where do you put your alpha particle, on the reactant side or on the product side? Reactant side. Okay, because it says when you react with alpha particle, right? Therefore, you know you should be able to write this. Alpha particle is what? Helium, 2 neutrons over all mass. The mass number is 4, right? So you should actually write these things out. You must know the alpha particle is this. Okay? And then it says the CF244 was produced, right? That means actually this guy needs to show on the product side. Okay. And it also say as well as 2 neutrons. That means actually your neutrons is also shown on the product side. Okay, so the things that you should really need to do is actually, can you translate the standards into this simple equation? Okay, so if you can do this, then you should know that the mass number sum of your reactor need to equals to a mass number sum of your product, right? So here, you should notice that the mass number of the neutron is 1, but I have 2 of it. Therefore, you can multiply the coefficient 2. Okay? So by doing this, you know your A has to equals to 242. Okay? And then your Z plus 2 should equals to what is the proton number of your CF? Yeah, so when you go back and check out your periodic table, then you know this one is actually 98 plus 2 times, there's actually no protons for your neutron. Okay? So once you do that, then you should be able to find out your Z will equals to 96. Okay. So once you find out your Z is equal to 96, right, you can actually go back to your PR table and check out the atoms as in 6 protons. Okay. So when you check it out, and you'll realize there will be the CM, right? And then you can put its mass number to 42. That will give you the final answer. Okay, so it's very simple operation. Okay, any question for this? No? Okay, then let's do another practice. Okay, it says D47 can undergo electron capture. What is the product of the nucleus? Okay, so you want to know the product, right? So the things you start with is V47, right? So undergo electron capture. Okay, so where should you put your electron? Reactant side or product side? Reactant side, right? Every time you see this pure capture, okay, absorption, and it is actually the things you need to put on the reactant side. Okay. So that's actually the things you need to translate from the description. Okay. So now you want to actually figure out what's the product, right? So in order to write out your product, you must know what is actually the ultimate photon number, right? So your first instruction, know the photon number of your vanadium, right? So what's the photon number of your V? 20, 23, right? Okay. So you know the product will have 23 minus 1, which is 22. Okay. So you have photon number of 22, therefore you know your atomic symbol will be titanium, right? And then your mass number will be 47 plus 0, there will be still be 47. Then there will be actually your product. Okay, so all you do is actually trying to read the sentence and understand what it means, translate into equations, and do this simple operation, you'll be able to figure out the answers. Okay, so let's actually how you predict whether an atom is stable or not. Okay. The second type of question I'm going to encounter for the homework this week or quiz this week is going to ask you if you have unstable nuclei, what kind of decay you are going to have. Okay, so how do you have to handle questions like that? So the basic idea is actually you want to use the N to Z ratio. Okay, so when I say N to Z ratio, that means actually your proton, the neutron number over your proton number. That's the N to Z ratio. Okay, so number of neutron over number of proton. Okay, so use that as your parameters to judge what kind of decay you're going to pass. All right. So everybody see this table, right? So this table again is my own creation. You're not going to see this table in the textbook or any other places. Okay, it's just like the LoRa and GRA actually for the student. Okay, so use this one will make your life a lot easier. Okay, so how do we use this? Okay, so depending on your Z, okay, Depending on your Z, here you can see that I group these things into 4 different groups. 1 to 20, 20 to 40, right? 40 to 83, and larger than 83. So those are 4 different groups, okay? And if you calculate your N to Z ratio, sorry, so for every single group, I assign different ratios, okay? So this is actually a setup, okay? You have 4 groups, each group has different threshold, okay? And the threshold is actually very easy, like 1, 1.25, 1.5, 1.6. They have the increment like 0.25. It's that the very last one, 1.6. Okay, so those are the thresholds for different groups. Okay, so why do I do this? It's because in your textbook, it never actually tells you what kind of decay you can actually predict based on numbers. Okay, it just gives you a very qualitative description. Okay, so what I do is actually I went through I went through actually tons of questions and went through many data in your textbook. Then I found, okay, those are the numbers that you probably can use and safely give you the correct answers. Okay, so you have to really memorize this threshold. Okay, so once you are given atoms, right, you can definitely calculate your N to V ratio. Okay, if your N to V ratio is larger than the threshold, okay, then the atom will undergo a beta decay. And it is going to produce one electron on the positive side. Okay, so as long as your entry ratio is larger than the threshold, then all you have is a beta decay. Okay, so it's actually the number one limiting factor. Okay. So what if it's actually smaller? Then depending on the group, you have different response. Okay. And the response is also pretty simple. If you are the things smaller than 83, okay, you can see there's actually a cut here. It's just 2 scenarios. Right, the top 3 actually all give you the same response. Okay, if you have your entropy ratio smaller than the threshold, which the threshold will actually change among your group 1, 2, and 3. Okay, but if it's smaller, then what you're going to have is either a positron emission or electron capture. Okay, so these are the 2 top decay that you're going to have. Okay. If you have larger than 83, and your N to Z ratio is smaller than the threshold, here will be 1.6. Then you're going to have a alpha decay. That means you're going to have a helium 2,4 on the product side. Okay, so this will actually summarize all the scenarios we have. So if you can understand this table and use it, then you have no problem to know what kind of decay you can check out for a given nuclear. Okay, so let's just refresh our memory again. So in my setup, there are 4 different groups, right? 1 to 20, 20 to 40, 40 to 83, larger than 83. Those are 4 groups, right? Threshold wise is 1, 1.25, 1.5, and 1.6. Okay, very easy to memorize, right? So if you calculate your entropy ratio for the assigned nuclei, this is larger than the threshold, then all you have will be beta decay. Okay, if it is smaller than threshold, okay, for group 1 and 3, you are going to have what? The positron emission or electron capture. If it's larger than 83, then you have alpha decay. Okay, so those are the possibilities. All right, so let's practice this. Okay, so before we go, let's just quickly refresh our memory. Okay, we have 4 different groups, right? So 1 to 20, 20 to 40, 40 to 83, and then larger than 83. Okay, threshold wise is 1, 1.25, 1.5, 1.6, right? So if it's larger than your threshold, then you have beta decay, right? And all here you have, if it's small, then you have positron emission or electron capture. And then if it's smaller than the threshold, you have alpha decay. Right? So these are the things that you need to actually have in mind. Then you can actually do all the question that we want to go through later. Yes. This two is actually indistinguishable. Okay, so why that's actually a case? So positron emission means you're going to add this on the product side, right? And that is actually equivalent to adding a -1 on the reactant side. So these two are actually equivalent. Okay, charge-wise, one is actually -1 on your reactant side, one is actually +1 on your product side. Okay, so this two is equivalent and indistinguishable. Therefore, pick one or the other. That's it. Okay. Okay, so with this, then let's do a few practice. First, Y95. Okay, so you know your first is what? You want to look for the proton number, right? What's the proton number of your Y? 39, right? Therefore, you know your threshold will be 1.25, right? You know that's actual threshold you want to use. Okay. So once you know your proton number is 39, then you should be able to calculate your mass number, which is equals to 95 minus 39. They're going to give you a number of 56. Okay. So once you have to 56, then you know your N to Z ratio will equals to 56 over 39, which equals to 1.44. Okay. So once you get a 1.44, compared to your threshold, you know this one is larger than your 1.25, right? Since it's larger than your threshold, therefore you're going to have beta decay. Okay, so it's larger than your threshold, therefore it's beta decay. Okay, so I think how you know what kind of decay that you're going to have. All right. This is how you use this table. And you have to get used to the concept or the logic of using this table. Okay. Let's do another one. The second one. EU 141. Right. Of course, the first step is to find out what is the photon number of your EU. 63? 63. Okay, so photon number 63. Therefore, you know your mass number will equals to 141. Not mass number, neutron number, sorry. 141 minus 63, that give you a number of 78. Okay, so this is 63. Therefore, you know you need to actually use threshold of 1.5. Okay, so you know your threshold is 1.5. your N to Z ratio here will equals to 78 over 63. Let's give you a number of 1.24. Okay, and 1.24 is smaller than 1.5. Okay, therefore the decay you're going to have is either positron emission or electron capture. Okay, so this is actually how you figure out what kind of decay that you have. Okay, so let's do one more practice. The third one asks you about the AT212, right? So again, what's the proton number of your AT? 85, right? Therefore, you know it's larger than 83, so the threshold you're going to use is 1.6. Okay. Your neutron number will be 212 minus 85. That give you 127. Okay, therefore your N to Z ratio will be 127 over 85. That's going to give you 1.49. Okay, so 1.49 is smaller than 1.6. Therefore, you're going to have alpha decay. Okay, so this is actually how you use the table to predict what kind of decay you're going to have. Okay. All right, so any questions so far? If not, then we are going to enter in the very last topic for today, right? Once we know what kind of decay that we have, the next is actually we want to know how fast it's going to happen, right? And the equation we're going to use is this first order decay rate law. Natural log AT over A naught equals to negative K times T. Okay. So everybody is familiar with this equation already. Okay, this actually things we got test in our midterm one. Okay, so the things I want to first emphasize is that what is K? Constant, the decay rate constant. Okay, what is actually A0? Initial concentration. Okay, so right now the things that you should have that's new in this chapter is that we're talking about decays, right? That's actually the total numbers or total volume of your substance that's undergo decay. Okay, so after certain time t, okay, this species, the amount of this species will decrease, right? So at time t, the amount of land remaining, okay, remember it's remaining species is your AT. Okay, so AT is actually that specific substance at time t. Okay, everybody finds the statement, right? Okay, so listen very carefully now. Okay, if I say uranium 238 undergo a beta decay, okay, it's going to produce pluton 239. Okay, everybody follow the things? Okay, Uranium-238 undergo a beta decay and eventually produce plutonium-239. Okay, which one is actually my A0? Uranium is actually your A0. Okay, so every time you see species A undergo a decay, produce species B, the A0 is the substance A. Okay, you have to translate the language into the things you can use in your equation. Okay. Second thing that's very important is that this AT is the remaining substance A. Okay, not the final decayed product. Okay, so that is actually the clear distinction that you must have. Okay, and the other thing I want to emphasize that is in this type of questions, you're going to see this term a lot. Okay, so in many questions, it doesn't want to tell you the decay rate constant K directly. Instead, very often you can see the half-life, the decay half-life time. Okay, meaning I give you a T half. Okay, so every time you see T half, all you need to do is what? First, back calculate your decay rate constant K. Okay, so that is actually a step you must do. Okay, because the eventual equation used will always be natural AT over A0 equals negative KT. There will always be the equation what to use with the final calculation. Okay, but in that calculation, you always need your rate constant K. But it's not going to tell you the K. It's going to tell you the T hat. Okay, so how do you actually get the K from T hat? Is using that K times T hat equal to 0.693. Right? How is this generated? It's actually very simple, right? The reason you got this equation is because at the T hat, what it means your AT is going to equals to half of your original amount, right? So you simply replace your AT with 1/2 of your A0, so that you got this. This T will become T half, right? Because right now the amount is 90 is half of the original amount. Okay. Then this will cancels out. If you put the negative sign to the left, you have A times your T half equals to negative natural log 1/2. Okay, if you put the negative sign inside here, it will be natural log 1/2 inverse, which equals to natural log 2, which will give you a number of 0.693. Okay, so that 0.693 is basic natural log 2. Okay, and the reason log 2 is because we are at specific time point, T half. Right now your concentration just half amount of the original. Okay, so let's actually nothing fancy about this equation. It's still the same equation, just the condition right now is your AT equals to 1/2 of your A0. Okay, so you can simply memorize this. That's fine. It's always true. K times your T half equals to 0.693. Okay, so every time you see this half-life, you know the thing to do is I have to calculate my K first. Okay, once you calculate your K, then you know later on you can just plug in that natural AT over A naught equals to negative KT. Okay. So how do we actually date a substance? Okay, we're going to use this equation. Okay. So what you need to do is actually every time you have this decay, okay, you will know what the decay product is, right? So you know how many decays occurred. Okay. So let's say, for example, you have 100 undecayed product A, and then later on it becomes 50. 50, let's do that. Okay, 40. Okay, you have 40 product remains. Okay, so and then you're going to produce 60 decayed product, right? So to get the original number, to get your A0, how you do is actually you just count the number of undecayed product plus the count of decayed product. Then you have your A0. Okay. Yeah. So and then you can also know how many have to remain, right? Therefore you have your AT over A0. If you know your K, then you can calculate your T. The T will be how old your original sample is. Okay, so let's actually basic graphic flow. Okay. One thing that you want to be very careful is that in your questions, you provide the mass of your undecayed product A and decayed product B. You cannot use the mass for this equation. You must use number of atoms or moles of atoms. Okay, and the reason is very simple because the decay is one-to-one transition. Okay, it's a single atom transition. Therefore, the number of atoms matters. Okay, it's not the mass of your atom, but numbers of atoms. Okay, therefore, when you use this equation, it must be either the mole or the total numbers of atoms. Okay, so those are the key concepts that we must have. Okay, so here you can see that I say if you have A is undecayed, things you can see in your substance. And then you have B as the decayed product. Okay, inside a rock. Okay, so to calculate your A0, you will be the number of A plus the number of B to get your A0. Okay, when the numbers, it can also be the moles. Okay, but it cannot be the mass. Okay, so that's very important. Okay, so with that, let's do a few examples so you can see how these things can be applied. Okay, so let's look at this first. It says cesium-137 undergo beta decay and have a half-life of 30 years. How many beta particles are emitted by a 14.0 gram samples in 3 minutes? Okay, so what's the keyword here? What's the keyword here? Half-life. Okay. And once you see the half-life, you know there's only one equation you can use. Natural log AT over A0 equals negative AT. Right? So that's actually going to be the center concept that we're going to use to solve this problem. All right? So make sure you actually know that. Okay? Of course, the question is asking what? How many beta particles, right? Will be produced. Okay, so on the description it says if let's say 1 decay, you're going to produce 1 beta particle. Okay, so all you do is actually want to know how many decays occur. Okay. So from the half-life, you also need to know the equation eventually we're going to use will be this. Okay, so data, you have CS137, you have 14 grain. Okay, and then you want to know how many beta particle will be produced after 3 minutes. Okay, and you have half-life of 30 years. Right, so those are the three information you get from the description. Okay, so remember I said just a couple of minutes ago, I said if you see the information of your t half, what do? Calculate the k. Okay, so start from later. Because you know your k times your t half equals to 0.693, right? Therefore, your k times t half is 30 years. Okay, but here I want to be careful because later on, you know, when you use this equation, let t you're going to use is 3 minutes, right? Therefore, the k has to be the same unit. Okay, so here is 30 years, right? Need to convert into minutes. So 1 year is 365 days, 24 hours, and 60 minutes. Okay, so that's your t half equals to 0.693. Therefore, you can calculate your k is going to equals to 4.4 times 10 to the negative 8 per minute. Okay, so that's actually the first things that you should get. Every time you see the t half, calculate the k. Okay. So now we know we want to use natural log at over a0 equals to negative k times t, right? We know our k now, right? We know our t. We do, right? Because we want to know after 3 minutes, right? Therefore, you know this t will be 3. Okay. So now come to the things a0 and at. Okay. So if you look at this question, what's the information that you get? 14 grain, right? To start with, right? So is that your AT or A0? A0, right? So that is actually things you want to put into your equation. Not exactly, right? Because we know when you put in the number into the equation, the number has to be either the mole or the number of atoms. Okay? It cannot be the mass. So right now the information we got is 14 grams is the mass of the sample, right? So if actually do some modification of that. So here eventually you want to know how many decays you're going to have, right? So actually first go down to, okay, how many particles I have to start with, right? So what you do is actually first to calculate the moles, which is 14 divided by 137. That's how many mole of cesium atoms that you have, right? But here, that's not where you should stop because you want to know exactly how many of them are decayed, right? Therefore, you have to first multiply the Avogadro number. Right, so that's how many particles, how many atoms that you have to start with. Okay, so it will be actually a gigantic number, right? So if you do that calculation, it will equals to 6.6.15 times 10 to the 22nd. Okay, so you have that many atoms to start with. Okay, and you want to know after 3 minutes, how many of length undergo decay, right? So how you do is actually you calculate how many of them are remains. And the difference between that number and then your original number will be how many atoms has undergo the beta decay, right? And that will give you the answer you are looking for. Okay, so therefore you put in natural log 6.15 times 10 to the 22nd. You want to know how many of them will remain undecayed. And the rate constant is 4.4 times 10 to the negative 8 after 3 minutes, right? So your AT is going to equals to exponential negative 4.4 times 10 to the negative 8 times 3 divided multiply 6.15 times 10 to the 22nd. Okay, so once you do that calculation on your calculator, you know your AT is going to equals to 6.149999188 times 10 to the 22nd power. Okay. Therefore, you know the decay will be A0 minus your AT, which equals to 6.15 times 10 to the 22nd minus 6.149999188 times 10 to the 22nd. Then you end up with a result of 8.12 times 10 to the 15. Okay, then there will be how many atoms will undergo the beta decay to produce your beta particle. Okay, any question for this? Yeah, so do you see how many digits I put over there? Do you see the sexual potential you're going to have a rounding problems? Yeah. Right? How to avoid that? You need to know how to set up your calculator right. Okay, if you want to get the full quality of the questions, so I write off it intentionally so you can see, oh my God, there's so many digits. Okay, so the reason I write this down is because you need to know how to operate your calculator right, properly, so you can get the correct answer out without an issue. Okay, so you can go home and practice, push your button, figure out what is actually the way that works for you. They can give you the correct numbers. Okay, so you must actually do these things at home so you know when you do this in casa, you'll be able to do it correctly. All right? Okay. Very last question today. Okay, it says a rock contains lead-206 for each milligram of uranium-238. Okay, it says the half-life of the decay of uranium-238 to lead-206 is that much years. Okay, then it asks you how old is the rock. That's a question that you can apply to any subject you want to know its age, right? So this is actually how scientists actually think the subjects. Okay, so here they use the uranium as example, right? But the most commonly used one is the carbon-13. Okay, so how much carbon-13 has decayed? They become carbon-12. Okay. So how do we actually understand and solve this problem? Again, keyword is what? Yes. That's a keyword, right? Therefore, you know you are going to use natural log AT over A0 equals to negative K times T, right? So the T half will tell you the K, okay? And then you want to know how old it is. That means actually you want to figure out the time, right? That means actually you should somehow figure out the ratio between your AT over A0. Right? So let's the things that we want to actually solve, then we can just solve for your T. Okay? So we know the Q is trying to solve the T. Okay. The data says you have the decay is always going from U238 becoming PB206, right? So which one is your A? Is it U or PB? U or PB is your A. We say this AT over A0, right? In the equation, the AT over A0, right? Here you have two substances. One is U, one is PB, right? Which one is your A? U, okay, make sure it's actually undecayed after it's your A. Okay. So I said a lot of things in the beginning, trying to actually make it more clear to you. Okay, so make sure you know who is actually the target you want to actually look for, right? So apparently this is your A, right? Okay, and it says in this rock, you have 0.275 milligram of PB per milligram of U, right? There is actually 1 milligram of U. You're going to have that much PB. Okay. So it tells you the mass, right? But I say you cannot use the mass for your AT and A0, right? You must either use the number of atoms or mole of atoms to do your calculation, right? So right now, you know, if you have U238, you have 1 milligram. Then your PB206, you are going to have 0.275 milligram, right? So we cannot use the mass. So what do we do? Calculate the mole first. Okay. So you should know that in this rock, you are going to have 1 times 10 to the negative third over 238. You have that many moles of your U, right? And then you are going to have 0.275 times 10 to the negative third over 206. Okay, so you have that many PB. Okay, so you have 11 more of your U and 11 more of your PB. Okay, so now what I want you to think. The U I have, okay, is U238. The U I have, okay, 1 milligram. Is that A T or A0? AT or A0? It's current, right? Is that okay? Now I have that much. That's okay. This is actually from many years ago, right? So that's your A0. So right now it's your what? Your AT. Okay. Therefore, you know this number will be your AT, right? How do you calculate your A0? Because the decay is always 1 to 1. Okay. So the AT means actually that's the remaining one. They are the ones that's not decayed. Right? The PB is what? PB is the decayed product. Right? And it's actually original, you have that much. You have this much got decayed. Right? So how do you calculate the original total number of your U? Will be the sum of the two. Does that make sense to you? Yeah. Therefore, you know your A0 will simply equals to 1 times 10 to the negative 3 over 238 plus 0.275 times 10 to the negative 3 over 206. There will be your A0. Okay. So once we actually understand what is my AT, what's my A0, then we can start to do this. Natural log AT, 1 times 10 to the negative 3 over 238, divided by your A0, which is this. Plus this. Equal to negative K. We haven't calculated our K yet, right? But we know the K, the T half is 4.5 times 10 to the 9 equals to 0.693. Therefore, your K will equals to 0.693 divided by 4.95 times 10 to the 9. That will give you a K of 1.54 times 10 to the negative 10 per year. Okay, so you have the K here, plug in here. So you have 1.54 times 10 to the negative 10 times your T. Okay, then you can solve your T. You're going to get a number of 1.79 times 10 to the 9th power. Okay, so this is actually how we think UNT. Okay. Again, here the key is that can you actually recognize who is actually your AT, who is actually A0, right? The idea is actually to calculate your A0, it must be the sum of your remaining undecayed product plus the decayed product amount. Okay, you must use either moles or number of particles to do the calculation. Okay, so that's it for today. Thanks.